Today I'm going to talk about solving polynomial equations using complex roots. The report contains three different parts: the fundamental theorem of algebra, the Vieta theorem, and examples of solving polynomial equations. The fundamental theorem of algebra gives that a polynomial of degree n with coefficients in C, the polynomial equation p of z equals 0 has a root in C. By the fundamental theorem of algebra, we can get a polynomial of degree n with coefficients in C, then the polynomial equation p of z equals 0 has n roots in C. Now I'm going to show how to prove the theorem by mathematical induction. First, we consider the base case with n equals to 1. We have p1 of z equals to a1z plus a0. So we get z equals to minus a0 over a1. So there's a one root for the polynomial equation. So we get the conclusion. It is true for n equals to 1. Then we consider the inductive hypothesis. We assume it is true for n equals to k. So we assume k-degree polynomial pk of z has k complex roots from R1 to Rk. Then we use inductive step. We will prove it. It is true for n equals to k plus 1. We consider the k plus 1 degree polynomial pk plus 1 of z by the fundamental theorem of algebra. There exists at least one root for the polynomial. We call it Rk plus 1. By the factors theorem, we can write the polynomial as pk plus 1 of z equals to z minus Rk plus 1 times q of z, where q of z is a k-degree polynomial. Now we apply inductive hypothesis. Q of z is a k-degree polynomial, so it has k roots from R1 to Rk. Thus, pk plus 1 of z with degree k plus 1 has k plus 1 complex roots from R1 to Rk plus 1. So we get the conclusion for any n and n degree polynomial equation has n complex roots. We also have an important theorem. P of z, a polynomial of degree n with coefficients in R. If alpha equals to a plus bi is a root of p of z equals 0, and at the same time b is not 0, and the conjugate of alpha is also a root of p of z equals 0. Now I'm going to show you how to prove the conjugate root theorem. First, we think about polynomial p of z, where all the coefficients are real. We consider a root alpha equals to a plus bi be a root of p of z equals to 0. When we plug in alpha into the polynomial, we get p of alpha equals to 0. We take conjugate on both sides of the equation. And we take the power out of the conjugate. Since our coefficients are all real, the conjugate of the real number is itself. So we get p of conjugate of a equals to 0. So a minus b times I is also a root of the polynomial p of z equals to 0. The Vieta theorem gives the relationship between the roots and the coefficients of the polynomial equation. Now we prove the Vieta theorem. We take the polynomial p of z with degree n. By the fundamental theorem of algebra, there are b1 to bn n roots of the polynomial equation p of z equals to 0. So we factorize it as p of z equals to an times z minus z1 times z minus z2 times z minus zn. To find the relationship between the coefficients, we first look at the z to the power n minus 1. To get z to the power of n minus 1, we multiply an with n minus 1 z and one of the constants z minus z1 to minus zn. So we get an minus 1 equals to minus en times the sum of all the roots. So the sum of all the roots equals to minus an minus 1 over an. Now we look at z to the power n minus 2. To get z to the power of n minus 2, we multiply an with n minus 2 z with 2 of the constants minus z1 to minus zn. So we get an minus 2 equals to an times the sum of all the 2 of the roots multiplied together. So we get the sum of zi times zj, where I and j from 1 to n equals to an minus 2 over an. So we get the generalized form of the weirdest theorem. The coefficient an minus k involves choosing k roots minus zi1 times 1 minus zi2 times 2 minus zik from all the roots z1 to zn. So the sign is minus 1 to the power of k. The general form of the weirdest theorem is zi1 times zi2 times zik, where I1 to ik from 1 to n equals to minus 1 to the power of k times en minus k over an. Now we look at our first example. Given that 2 minus I is the root of the equation, and all the coefficients are real, how to find the value of a and the other roots of the equation? Since all the coefficients are real, 2 minus I is a root, and 2 plus I is also a root. By the factors theorem, we can factorize p of z into z minus 2 minus I times z minus 2 plus I and q of z, where q of z is a polynomial of degree 2. And we use long division to get p of z can be expressed as two polynomials of degree 2 multiplied together and a tail of a plus 12 times z. And by the factors theorem, p of z should be factorized and the tail should be 0. So we get a equals to minus 12, and we can get the other two roots. The second example is given that the three roots of the equation are alpha, beta, and gamma. Find the sum of the three roots, and we can directly apply the Weber theorem to get the sum of the three roots is minus a and minus 1 over an, so it's minus 6. So that's how to solve polynomial equations using complex roots.